All right, we're going to go ahead here with chapter 2. I apologize about missing today, and this video might be a little bit longer because there's quite a few slides here, but there should be a lot of review material, but we're getting into linear and quadratic functions today, things that we have talked about and have done, but just understand that we're talking about polynomial functions. Okay, what a polynomial looks like in mathematical terms is a sub n x to the n. This is the largest exponent, and this is just the leading coefficient. Plus a sub n minus 1, that's just the next smaller variable here, next smaller degree. So it just keeps going down until you get to eventually a constant. A sub 0 is the constant. So we have a polynomial of degree n. So again, what this would look like if I gave you a problem uh, in class looks something like this, okay, where we have the highest degree, in this case would be 4. The polynomial means many. There could be infinite different values that I could put here, degrees that I could put here. So that's why we have this long, drawn-out mathematical equation for polynomial. But key characteristics we need to know: for it to be in standard form, it has to go from largest to smallest degree. And the leading coefficient is always the number in front of the highest degree. So even if I gave you this same exact polynomial that looked like this, okay, same exact numbers here, right? This is not the leading coefficient. The leading coefficient would be this 3 because it's the number in front of the largest degree, okay? And then we have the 0 function. F of x equals 0 is a polynomial function. It has no degree and no leading coefficient. So we're going to go through a few of these. I'm just going to ask you, is this a polynomial or not? Well, what makes it not a polynomial? If you see any negative exponents, it's not a polynomial. If you see anything underneath a square root or any fractional exponents, it's not a polynomial. So this right here is a polynomial because the degree is 3, degree 3, degree 1, and degree 0 of my constant term. So this would be yes. This one right here is not a polynomial because x is raised to a negative exponent. So no. This one right here, if I rewrite this, you might recall from Algebra 2 that this is the same exact thing as this, which means it's raised to the 1/2 power. So this is a no. You can't have fractional exponents. And then this one, even though it's not in standard form, this is a yes. Degree 4, degree 1. So that would be a yes. So again, this book kind of likes to listen to itself talk. It gives a bunch of information on certain slides. So as I'm going through this, you might want to just pause it. I'm not going to read everything for you. Uh, but what we're really going to focus on today is linear functions and quadratic functions. We have something called a 0 function. The form is f of x equals 0. The degree is undefined. This is if you have a function that's just equal to the number 0, the degree is undefined. If you have just a number, then we say that degree is 0. A linear function, ax plus b is equal to 1. We're very accustomed to seeing it like this, mx plus b, where this a and this b is our slope, okay? So we're going to look at the linear function and the quadratic function today. So looking at this first example here, okay, I'm going to talk about 3 different formulas here that you're going to need to know, write down, have access to, but you should have seen them before. First of all, it says write an equation for the linear function such that f of negative 1 equals 2 and f of 3 equals negative 2. This is a fancy way for me to write an ordered pair, right? This is my x value, that's my y value. This is my x value, that's my y value. So if you don't like the way this notation is, write it like this: negative 1 comma 2 and 3 comma negative 2, where this is my x1, this is my y1, this is my x2, this is my y2. The first thing I'm going to do if I'm going to write a linear function is I need to know what the slope is. Okay, so I have to find the slope. Well, what's the formula for slope? y2 minus y1 over x2 minus x1, which is negative 2 minus 2 all over. If I put this negative 2 first, I have to use the x2 first, so 3 minus a negative 1. Minus a negative turns into a plus. Please look at the formula. There's a minus sign in each of these. Why did this stay a minus? Because I was plugging in a positive number. Why did this minus right here turn into a plus? Because I plugged in a negative. So I got negative 4 over 4, which is equal to -1. Once I have the slope, I'm going to plug this into my point slope form, okay? I'm sure that you have seen this in Algebra 1. Y minus y1 equals m times x minus x1. So I have y, I'm going to use just this first point right here, minus 2, right? Notice how that stayed a minus because I plugged in a positive, equals, I just found m, which is -1, times x, and I'm going to plug in a -1, so minus a -1 turns into a +1. So there's 2 steps to solving this. I'm going to distribute, and I get y minus 2 equals -x minus 1. I'm going to get y by itself. I'm going to add 2, and I get y equals -x plus 1. This is the linear form that I'm looking for, which of course is y equals mx plus b. Okay, now some of you, and I believe Miss Thomas teaches this, you may have just had this formula right from the beginning, and you may have plugged this value right here in for y. We found x, or the slope, to be -1, so we may have plugged in a -1 for m. And again, if you don't know, if you've never done this before, just see that it works. What was my x value? -1 plus b. I'm trying to find b here, so I have 2 equals -1 times -1 is 1 plus b. I subtract 1, and I get 1 is equal to b. Well, that's what I got here. So you could have replaced the b and the m this way using this formula. So with linear equations, this is what we need. We're going to talk a little bit about association, correlation, and linear modeling. I'm not going to talk a whole lot about this. I'll let you read it. You can pause it and read it. But understand, if you're given a set of ordered pairs, it could form different shapes. Um, could form different shapes. And we say that linear association between variables could have positive linear association if the data is going from left to right, is going up, and it's negative if it's going down. So take a look at some pictures here just to get an idea. In statistics, we talk more about the strong and the weak correlation, but if you can see that clearly that this data right here is set of order pairs, doesn't form a straight line, but I could draw a line through that, and it's a pretty strong positive linear association. This one, same thing, the data is going up as we go to the right, but it's the points kind of vary further and further away from the dots. This one, it's all over the place. I couldn't draw a line that through that data. This one here, as the data goes further to the right, it gets smaller and smaller, so that's a pretty strong negative linear correlation, and this one also pretty strong uh, negative correlation. So be able to explain weak positive, strong positive, weak negative, negatives going down from left to right, positives going up from left to right. Okay, so now this is the slide I would write down. We have the correlation factor, correlation coefficient R. The closer R is to 1 or -1, the stronger the association. So when we're talking about this R, if R is greater than 0, then we have a positive linear association. If it's less than 0, then it's going to be a negative linear association. Okay. If R is close to 1 or -1, that's what this is saying, the absolute value. Okay. If it's close to -1, then that would mean that there's a positive, or I'm sorry, a negative strong correlation. If it's closer to +1, then there's a strong positive correlation. And if R is equal to 0, that would look like this graph right here where the data is kind of all over the place. So this R would be closer to 1. This R would be closer to -1. Okay. So we're going to take a look at an example here. I'm going to need you to write this formula down because this is what we're going to plug into Desmos. It's going to be Y, a little tilde. If you look at your Chromebook, it's up in the left-hand corner of your keypad. You'll hit Shift and you'll hit that little tilde button. So it's got to be Y1 tilde AX1 plus B. This is the formula we're going to use once I enter all of this data right here. Okay, so to write the linear equation, I'm going to show this on Desmos. I'm going to enter all this data right here into Desmos. Okay, so it's going to pop back up. How do I get a blank table? I hit this little plus sign. and I get a blank table, I'm going to enter in all of the x values, from this right here. So 2.4, 2.6, and I'm going to go down and enter all those into Desmos. So 2.4, 2.6, so 2.4, 2.6, 2.8. Look, it kind of fills it in for you all the way up to what was my last one? It was 3.6. So there's the 3.6. Now I have to fill in all of the y values. Might take me a second, but 38,320. So 38,320. 38,320. Don't use commas. It'll tell you don't use commas. 33,710. 28,280. 26,550. 25,530. And I would recommend you trying to do this and make sure you get what I get, 22,170. As you can see, you don't see any of these dots on Desmos right now because they're way the heck up higher. 18,260, 18,260. Okay, but here's all those dots. If I scrolled way the heck out, you would see these dots are way, 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 way. See if I can keep zooming out way the heck up here, right? It almost looks like a straight line, but if I got closer to these and zoomed in, we know that they're getting bigger just slightly. Okay, so now if I plug in Y1, I hit the little tilde, look at the symbol, make sure you hit that, A, X1 plus B. Notice that I get an equation right here, okay? It tells me what my slope is and what my y-intercept is. So when I ask for a linear regression line, this is what we would plug in, y equals negative 15,358.9 plus 73,622.5. Again, this is my linear regression. Don't forget your x here. Whoops. Okay, this would be my linear equation. So if they ask for the linear equation, this is where I get it from. Look at my correlation factor. R is negative 0.98. I'd say that's a pretty strong negative correlation, right? Because it's really close to -1. So now, the second part of this problem asks you to find the values when what? Then use the model to predict weekly cereal sales if the prices drop to $2 or raise to $4. So you could take the $2 and plug it in here for X, get an answer. Take the $4, plug it in here for X. You can also hit this little gear button and get a table. And we wanted to know when it was what? $2? Well, that would be 42,904. We also wanted to know when it was $4, right? That'd be 121,086. I'm sorry, 12,186. So you get the two answers using Desmos. Okay. So that right there is the linear equation component of this section. I'm going to start a new video, make another video for the quadratic functions.